Welcome to Everything Matters, Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element cadmium. Here I have a sample of cadmiums for you to see. It's kind of a silvery element. Let's get back to our presentation. Here we see the beautiful periodic table produced by Theodore Gray. Incidentally, Theo has written one of my favorite books called The Elements. You can pick it up from the online Exploratorium store if you'd like. Check out his fantastic site, periodictable.com. Cadmium is the 48th element in the periodic table. Its atomic number is 48 because that's how many protons are in its nucleus. The number of protons in a nucleus determines which element we're talking about. Cadmium was discovered simultaneously in 1817 by Friedrich Strohmeyer and Carl Samuel Leberecht Hermann, both in Germany. They discovered it as an impurity in zinc carbonate. That zinc carbonate is found in nature as the mineral smithsonite, historically called calamine, an old name for zinc ores. Incidentally, calamine lotion is a mixture of zinc oxide, not zinc carbonate, with a little bit of iron oxide and is really unrelated to this zinc ore. Cadmium is obtained almost exclusively as a byproduct of zinc smelting and, to a lesser extent, of lead and copper smelting. Smaller quantities are also produced by the recycling of iron and steel. Cadmium is from the Latin cadmia, or Greek cadmia, meaning calamine. That was named after the Greek character Cadmus, the mythological founder and first king of Thebes, who we see here fighting the dragon in a painting by Hendrik Goltzius. From this rich history, we get the name of the element cadmium. Cadmium belongs to a large group of elements in the middle of the periodic table called the transition metals. These elements are defined as ones with an incomplete d shell of electrons. This is also known as the d block of the periodic table. Cadmium is the last element in its row that's a member of the d block, though there is some debate among chemists as to whether cadmium really belongs in that d block. The universe produces some cadmium in merging neutron stars, pretty exotic, with about equal amounts also produced in dying low-mass stars. Here on Earth, the main suppliers of cadmium are, not surprisingly, also the main suppliers of zinc. China, with almost 1/6 of the world's cadmium production, is closely followed by South Korea and Japan as the major suppliers. Use of cadmium has grown steadily since 1900. The world now produces about 25,000 metric tons per year, and this figure does not include U.S. production, whose production numbers are withheld for some odd reason. Some zinc ores contain up to 1.4% cadmium. In the 1970s, the output of cadmium was 6.5 pounds of cadmium per ton of zinc. The American Chemical Society's endangered element list places cadmium as, quote, limited availability, future risk to supply, unquote. So we need to keep our eye on this and be sure to recycle our cadmium carefully. Not only because it's relatively rare, but also it's highly toxic. How common is cadmium? Not very. Let's see. It's the 58th most common element in the universe, the 42nd most common element in the Sun, the 48th most common element in meteorites, the 66th most common in the Earth's crust, a little more common in the oceans at 45th most common element. That actually accounts for about 8 million tons of cadmium, about the same as the amount of gold in the ocean, 8 million tons of gold in the ocean as well. It's the 22nd most common element in humans. More on that later. Cadmium, despite its limited abundance, is actually pretty cheap, a little less than $3 per kilogram in large quantities. If you had invested in cadmium about 5 years ago, you would have made a tidy profit. It's almost doubled in price during those 5 years. That's about 14% per year increase on the average. That's a pretty decent return on investment. If we compare the size of the cadmium atom to that of hydrogen, we'd see something like this. Most of the transition elements in that D block have similar sized atoms. Here, our atom size is sorted from largest, cesium at the left, to helium, the smallest on the right. You can see that cadmium is pretty close to the middle of the pack. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same. 48 protons for cadmium, like we mentioned, but there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes, and they're chemically identical, but with slightly different weights. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 38 isotopes of cadmium, and of these there are 6 stable non-radioactive isotopes: cadmium 106, 108, 110, 111, 112, and 114. They occur in various abundances in nature. But if you add up the 6 stable isotopes, you don't get 100%. You get close to 80%. The radioactive isotope cadmium-113 and cadmium-116 account for the rest. We'll see why in the next slide. By the way, the word isotope comes from the Greek isos, meaning same, and topos, meaning place, since they all occupy the same place in the periodic table. Of the radioactive isotopes of cadmium, these are the longest lived, the ones with half-lives all over 1 hour. If you wait for 1 half-life, half of the isotope you have will decay. If you wait for 1 more half-life, half of that half decays, leaving you with 1/4, and so on. As you can see, the longest half-lives here are for those 2 isotopes making up about 20% of the existing cadmium. Cadmium-113 has a half-life of 8 times 10 to the 15th years. That's 583 times the age of the universe, while cadmium-116 has a half-life of 2.8 times 10 to the 19th years, or over 2 billion times the age of the universe. So you see that not much of either of those isotopes has had enough time to decay significantly. Cadmium is moderately dense at 8.65 grams per cubic centimeter. Remember that water has a density of 1 gram per cubic centimeter. I've put up a couple more densities for comparison. Cadmium is slightly denser than iron at 7.8 grams per cubic centimeter. Here is a graph of the elements from highest density on the left to lowest density on the right. When we do this talk at the Exploratorium, we have a set of blocks so you can feel the effects of density yourself, but we'll have to wait to do this until we're back in the museum. Our set of blocks have a wide range of densities, with the heaviest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, to magnesium. We also have a plastic and wood block, but those are not technically elements. Again, cadmium's density is 8.65 grams per cubic centimeter, just above iron, and below copper, making it the 36th densest element. Cadmium has the 73rd highest melting point on this chart, with a melting point of 321 degrees Celsius. Pretty low. There are only 16 other solid elements that melt at lower temperatures. Cadmium also has the 73rd highest boiling point, at 767 degrees Celsius. Its boiling point is only 446 above its melting point. There are only 4 other metal elements known to have a smaller difference between the melting and boiling points. Those would be magnesium, thulium, mercury, and ytterbium. Cadmium is slightly exceptional because it has the seventh highest thermal expansion rate, 3/100,000ths per degree Celsius. That means that if you had a 1 meter bar of cadmium, it would get longer by 3/100,000ths of a meter, or 3/100ths of a millimeter, when you raised its temperature by 1 degree Celsius. I know that doesn't sound like much, but it does add up when you change the temperature significantly or you have a long bar of cadmium. Cadmium is a very soft solid with a hardness of only 2 on Mohs scale of hardness. You might be able to scratch this metal with your fingernail, it's so soft. In this chart of hardness, sorted from hardest on the left, boron, to softest on the right, cesium, cadmium is the 43rd hardest and 24th softest element. Cadmium is the 15th best conductor of electricity. No slouch, but it wouldn't make very good wire either. With its higher resistance, you'd waste most of your electricity in heat it would generate. Plus, remember that it melts at a very low temperature. Electricians frown on melty wires. Cadmium is the 19th best conductor of heat. Again, not bad, but not really good enough to use for this purpose either. From our periodic table of the spectra, we see that cadmium displays a variety of emission lines across the spectrum. What's not obvious from this picture is that most of the light comes from the green and blue end of the spectrum. The bright lines given off by cadmium are seen all combined in this special cadmium lamp. When the lamp is first turned on, you see the purplish glow of argon gas. This gas vaporizes the solid cadmium in the glass tube, and you then see its beautiful bluish-green glow. The biggest use of cadmium is, or was, in the making of rechargeable batteries. Here, we see a variety of nickel-cadmium batteries. The disadvantages of these is that they had a limited number of charge-discharge cycles before they would no longer hold a charge. And the fact that the toxic nature of cadmium meant we had to be very careful to recycle them properly. They also had a fully charged voltage of only 1.2 volts, making them unsuited in some voltage-sensitive applications as direct replacements for the more common 1.5 volt carbon-zinc batteries of the same sizes. Electroplated cadmium, banned in most circumstances because of the metal's toxicity, functions as a sacrificial coating, corroding before the substrate material. Cadmium plating's main use is in aeronautical applications. Compounds containing cadmium were used as a phosphor in black and white television picture tubes to create the white light forming the picture we watched. Different cadmium compounds were used in color televisions to create the green and blue glowing phosphors. Of course, now that we've moved beyond picture tubes, that use is only academic. Here's how it worked. Electrons boiled off the heated cathode in the neck of the tube are accelerated, focused, and bent to strike the cadmium oxide phosphor screen to create the white glow we looked at. In 1860, Barnabas Wood announced the discovery of an alloy of bismuth, lead, tin, and cadmium in proportions such that it had a very low melting point. Wood's metal melts at a low 70 degrees Celsius or 158 degrees Fahrenheit. A nice cup of tea would melt a spoon made of this, but I wouldn't drink that tea. Not only does Wood's metal contain toxic cadmium, but also poisonous lead. Here, you see a small ingot of Wood's metal melting in a hot beaker of water. In a nuclear fission reactor, rods of cadmium are used to absorb neutrons. Those neutrons are responsible for the chain reaction, causing the nuclear material in the reactor core, usually uranium, to break into smaller atoms, releasing tremendous amounts of energy. Pulling the rods out of the core allows more neutron reactions to take place, heating up the core. Pushing the rods in slows the reaction, cooling the reactor, hence control rods. In 1907, cadmium became the standard by which length was measured. In that year, the International Union for the Cooperation in Solar Research, which later became the International Astronomical Union, defined the international angstrom by declaring the wavelength of this red line of cadmium equal to 6,438.4696 international angstroms. This definition was endorsed by the International Bureau of Weights and Measures in 1927. By the way, the angstrom unit is named after the Swedish physicist and one of the founders of the science of spectroscopy, Anders Jonas Angstrom. The angstrom unit is 10 to the minus 10th, or 1/10,000,000th of a meter, pretty small. However, in 1960, the definition of both the meter and the angstrom were changed to use the element krypton instead. Poor cadmium. Cadmium sulfide is used as a yellow pigment, called cadmium yellow, and cadmium selenide, or in this case, cadmium selenosulfide, is used as a red pigment, often called cadmium red. This is a photocell, or a photoresistor. The electrical resistance of a photoresistor decreases with brighter and brighter light intensity, allowing more current to flow when it's brightly illuminated. It can change its resistance by a factor of up to 10,000, going from darkness to light. This is the electronic symbol for the photoresistor for the next time you find yourself reading a schematic. The photoresistor gets its light sensitivity from cadmium sulfide, the same ingredient in the pigment cadmium yellow. Cadmium selenide quantum dots, or QDs, are nanoparticles that fluoresce in a variety of colors determined by the size of the particle. The same exact material, cadmium selenide, is in each vial of liquid here. Only the size of the particles is different and is used to tune the color. Those sizes are labeled above the vials in nanometers, or billionths of a meter. These vials are being illuminated with an ultraviolet light to make them fluoresce. This has some interesting applications. For instance, in making LCD panels, one can make the colors from the TV brighter and more saturated with the use of a quantum dot panel that emits light at just the right colors to more efficiently pass through the red, green, and blue filters in front of the liquid crystals. Relatively low in cost, cadmium and tellurium can be compounded into cadmium telluride thin-film photovoltaic modules. Unlike silicon solar cells that use actual bulk slices of silicon, these only use a thin, vapor-deposited film, so they use much less material and are hence cheaper to manufacture. The thinness means that you can deposit the film on flexible materials like you see here. This also adds some unique manufacturing possibilities over the rigid and brittle silicon cells. One of the early lasers developed was the helium-cadmium laser. It put out a very deep violet beam of light, very different than the much more common red of the helium-neon or HeNe laser. Cadmium plays no natural biological role and should not normally be found in the human body. Cadmium and its compounds are highly toxic, and exposure to this metal is known to cause cancer. Cadmium targets the body's cardiovascular, renal, gastrointestinal, neurological, reproductive, and respiratory systems. Is there a system it doesn't attack? Of course, cadmium is found in the human body because of environmental pollution, but thankfully in small quantities. We'll end today's talk with Mary Soon-Lee's elemental haiku about cadmium. To find the angstrom, until Krypton ousted you, now looking for work. Thank you for watching Everything Matters, Tales from the Periodic Table. The next program in this series will examine another very interesting element, indium. We hope you'll join us. This program, like all Exploratorium programs, is only possible because of donors like you. We know that this time is challenging, but if you can, help us keep educational content like this free and accessible to all by donating today at www.exploratorium.edu/connect. Thank you.